Unit 3 The Cost Evaluation of Distributed Generation (DG) Systems over time involves analyzing historical trends, current market conditions, and future projections. Here's a breakdown. 1. Past DG costs. High equipment costs. Early DG technologies, such as solar PV, wind turbines, and gas-based generators, had high capital expenditures, CapEx, due to less mature manufacturing and limited economies of scale. Higher fuel costs. Diesel generators, DG sets, dominated, leading to high operating costs due to fuel price volatility. Limited grid integration. Energy storage was expensive, and smart grid solutions were underdeveloped, making integration challenging. Government incentives. Many countries, including India, introduced subsidies and feed-in tariffs, FITs, to support solar and wind power. 2. Present DG costs. 2024, declining CapEx. Costs of solar panels, wind turbines, and battery energy storage systems, BESS, have dropped significantly due to improved technology and mass production. Lower levelized cost of energy, LCOE. Solar and wind DG systems are now competitive with traditional grid power in many regions. Energy storage advancements. Lithium-ion batteries and other storage solutions are becoming more affordable, aiding microgrids and peak load management. Regulatory support. Policies like net metering, renewable energy certificates, RECs, and carbon credits incentivize DG adoption. Hybrid DG solutions, integration of solar, wind, and energy storage with traditional DG units optimizes costs and efficiency. 3. Future DG costs, projections, further cost reductions. Solar PV module prices expected to decrease due to advancements in perovskite and bifacial solar cells. Energy storage prices will drop with solid-state battery innovations. Wind energy costs may stabilize, but offshore wind will become more competitive. Rise of green hydrogen. Hydrogen-based fuel cells may replace diesel generators, reducing emissions and fuel dependency. Increased AI and IoT integration, smart grid solutions, predictive maintenance, and automated DG management will optimize operational costs. Decentralization and peer-to-peer, P2P, energy trading. Blockchain-based P2P energy trading may reduce dependency on centralized utilities, lowering overall costs. Policy and carbon pricing. More stringent carbon pricing could make fossil fuel-based DG less viable. Pushing renewables forward. Grid interconnection issues and need for renewable energy integration in India. India's power sector is undergoing a significant transformation as the country aggressively moves towards renewable energy, RE. With a target of 500 gigawatts of non-fossil fuel capacity by 2030, integrating large-scale solar and wind power into the national grid is critical. However, several grid interconnection issues pose challenges to seamless reintegration. This document explores these challenges and highlights the need for strategic solutions. 1. Grid interconnection issues in India. Despite substantial renewable energy capacity additions, India's power grid faces multiple technical, infrastructural, and regulatory challenges in integrating resources. Variability and grid stability issues. Intermittent supply. Solar and wind energy generation depend on natural conditions. Solar generation drops at night, and wind speeds vary, making resupply unpredictable. Frequency and voltage fluctuations. Sudden changes in regeneration can cause voltage instability and frequency deviations in the grid. Reactive power issues. Wind and solar plants generate less reactive power, which can impact grid stability. Transmission constraints and grid congestion. Location mismatch. Solar and wind projects are concentrated in states like Rajasthan, Gujarat, Tamil Nadu, and Karnataka, while major power demand centers are in Delhi, Maharashtra, and Uttar Pradesh. This geographical mismatch creates transmission bottlenecks. Inadequate transmission infrastructure. The existing high-voltage transmission network is not fully equipped to handle increasing repenetration, leading to transmission congestion. Delays in Green Energy Corridor (GEC) projects. The planned transmission corridors for renewable energy evacuation face land acquisition and financial challenges. See renewable energy curtailment of wind and solar power. Due to grid congestion and lack of demand flexibility, utilities sometimes curtail regeneration. Example, Tamil Nadu, India's largest wind power producer, often curtails wind power during peak generation periods due to grid limitations. Lack of energy storage solutions. Without large-scale battery storage, surplus renewable energy cannot be stored for later use. D. Challenges in rooftop solar and distributed generation. DG. Resistance from DISCOMs. Distribution companies, DISCOMs, often oppose net metering policies as they fear revenue losses from consumer-generated electricity voltage rise issues. High penetration of rooftop solar in local grids can lead to overvoltage problems, requiring smart inverters and power electronics. Limited smart grid deployment. Lack of real-time monitoring and two-way power flow management hampers distributed reintegration. Energy storage and flexibility issues. Battery energy storage systems, BESS, are expensive. Large-scale deployment of lithium-ion batteries is still costly, though prices are declining. Pumped hydro storage, PHS, is limited. India has some PHS capacity, but scaling up is slow due to geographical constraints. Lack of grid flexibility. India's grid is largely designed for centralized thermal power plants, not decentralized renewable sources. 2. Need for renewable energy integration. Achieving India's renewable energy goals, 500 gigawatts non-fossil fuel capacity by 2030 to meet climate commitments. Net zero by 2070. Requiring a transition away from coal. Round-the-clock, RTC, renewable power, combining solar, wind, and storage, is essential for energy security. B. Economic and environmental benefits. Lower electricity costs. Solar tariffs, 2 rupees minus 2 rupees and 50 paise per kilowatt hour, cheaper than coal, 4 rupees and 50 paise per kilowatt hour. Wind tariffs, 2 rupees and 50 paise to 3 rupees per kilowatt hour. Reduced coal import dependency. India can save billions in foreign exchange by reducing coal imports. Reduced carbon emissions. Large-scale reintegration will cut carbon dioxide emissions and improve air quality. C. Energy security and rural electrification. Decentralized resolutions, solar microgrids, distributed generation, can improve rural electrification. Microgrids and local storage can help remote areas achieve energy independence. 3. Solutions for grid integration of renewables. A. Energy storage deployment. Battery energy storage systems, BESS, for grid stability and peak load balancing. Pumped hydro storage, PHS, to store excess wind, solar energy. Green hydrogen as a long-term energy storage solution. B. Expansion of green energy corridors, GECs, dedicated transmission corridors for renewable energy evacuation, strengthening HVDC, high voltage direct current, transmission to transport power efficiently across states. See smart grid development and AI-based forecasting. Real-time forecasting and scheduling of solar and wind power to match demand-supply balance. AI-based predictive analytics for grid operations. Smart meters and demand response systems to improve grid flexibility. D. Hybrid renewable energy systems, solar-wind hybrid plants to balance intermittent power generation. RTC renewable energy, round-the-clock, contracts, combining RE with storage. A. Decentralized energy and peer-to-peer, P2P, energy trading, blockchain-based energy trading to allow local solar producers to sell power directly to consumers. Microgrids and virtual power plants, VPPs, for community-driven energy solutions. Power grid, electrical grid or power grid is defined as the network which interconnects the generation, transmission and distribution unit. It supplies the electrical power from generating unit to the distribution unit. A large amount of power is transmitted from the generating station to load center at 220 kV or higher. The network formed by these high voltage lines is called the supergrid. The supergrid feeds the sub-transmission network operating at 132 kV or less. Components, power plants, these are the sources of electricity, generating power from various sources like coal, natural gas, nuclear, or renewable sources. Transmission lines, high voltage power lines that carry electricity over long distances from power plants to substations. Substations. These are locations where the voltage of electricity is stepped down or up to match the needs of the distribution system. Distribution lines. Lower voltage lines that carry electricity from substations to individual customers. Function. The power grid's primary function is to efficiently and reliably deliver electricity to consumers, balancing the supply and demand for power. Importance. A reliable power grid is essential for modern society, powering homes, businesses, and industries, and supporting economic activity. Examples. In India, the Power Grid Corporation of India Limited, Power Grid, is a major player in the transmission of bulk power across the country. Types of electrical grid. The power station of the grid is located near the fuel source, which reduces the transportation cost of the system. But it is located far away from the populated areas. The power which is generated at high voltage is stepped down by the help of step-down transformer in the substation and then supplied to the consumers. The electrical grid is mainly classified into two types. They are 1. Regional grid. The regional grid is formed by interconnecting the different transmission system of a particular area through the transmission line. 2. National grid. It is formed by interconnecting the different regional grid. Reason for an interconnection. The interconnection of the grid provides the best use of power resource and ensures great security to supply. It makes the system economical and reliable. The generating stations are interconnected for reducing the reserve generation capacity in each area. If there is a sudden increase in load or loss of generation in a zone, then it borrows from the adjacent interconnected area. But for the interconnections of the network, certain amount of generating capacity known as the spinning reserve is required. The spinning reserve consists generator running at normal speed and ready to supply power instantaneously. Types of an interconnections. The interconnection between network is mainly classified into two types, i.e., the HVAC link and HVDC link. Point 3. Lower grid congestion. Decentralized generation reduces stress on transmission infrastructure, delaying the need for costly grid expansions. 4. Environmental benefits. Renewable DG sources, solar, wind, biomass, reduce carbon emissions and dependency on fossil fuels. 5. Energy cost savings. DG can provide cost savings through net metering, demand response programs, and reduced energy purchases from the grid. 6. Improved power quality. DG units, especially those with energy storage, can provide voltage support and frequency regulation. 7. Economic growth and job creation. Increased adoption of DG promotes local economic activity and employment in renewable energy sectors. Cons of DG interconnection. 1. Intermittency and variability. Renewables like solar and wind are intermittent, requiring backup solutions or energy storage. 2. Grid stability issues. High DG penetration can lead to voltage fluctuations, reverse power flow, and protection coordination issues. 3. High initial investment. Setting up DG units, e.g., solar panels, microgrids, involves significant capital costs. 4. Regulatory and technical barriers. Interconnection standards, utility approvals, and compliance with grid codes can be complex and time-consuming. 5. Limited control by utilities. Increased DG penetration reduces utility control over power generation, affecting grid management and revenue models. 6. Storage and infrastructure limitations. Energy storage solutions, e.g., batteries, are still expensive and require technological advancements for wider adoption. 7. Harmonization with existing grid. Integrating DG with centralized power plants and ensuring smooth operation requires investment in smart grid technologies. Regulatory framework for DG interconnection in India. India's regulatory framework for distributed generation, DG, interconnection is evolving to accommodate the growing share of renewable energy and decentralized power generation. Here are key aspects of the framework. 1. Policy and regulatory bodies. Ministry of Power, MoP, oversees national energy policy and DG integration. Central Electricity Regulatory Commission, CERC, sets regulations for interconnection, tariffs, and grid codes. State Electricity Regulatory Commissions, SERCs, define interconnection policies at the state level, including net metering and open access regulations. Bureau of Indian Standards, BIS, and Central Electricity Authority, SA, provide technical guidelines and safety standards for DG interconnection. 2. Key regulations and policies. A. Net metering and gross metering policies. Net metering. Consumers with rooftop solar PV or other DG sources can sell excess power to the grid, offsetting their electricity bills. Gross metering. Consumers sell all generated power to the grid at a fixed tariff and buy electricity at retail rates. State-wise variability. Each state has its own net metering capacity limits and tariff structures, e.g., Maharashtra has a 1 megawatt limit, while Delhi has a 5 megawatts limit. B. Electricity Act, 2003 promotes open access, allowing large consumers to buy power from DG sources directly, encourages renewable energy integration and decentralized distribution, allows third-party owned distributed generation projects under power purchase agreements, PPAs. C. Renewable Energy Policies. National Electricity Plan, NEP, and Renewable Energy Roadmap set targets for DG penetration. State renewable energy policies offer incentives like capital subsidies, tax benefits, and viability gap funding for DG projects. D. Technical Standards for Grid Interconnection. SAS, Technical Standards for Connectivity of the Distributed Generation Resources, Regulations, 2019 Mandate Guidelines for Voltage, Frequency, Islanding Protection, and Reverse Power Flow Management. SAS, Measures Relating to Safety and Electric Supply, Regulations, 2010 ensure safety and reliability compliance. 3. Challenges in DG interconnection regulation. State-wise regulatory variations, policies differ across states, leading to inconsistencies in tariffs and approvals. Grid integration issues, voltage fluctuations, grid congestion, and lack of smart grid infrastructure pose technical hurdles. Slow approval processes, interconnection approvals from DISCOMs and regulatory bodies can be time-consuming. Storage and ancillary services, limited regulatory clarity on battery storage incentives and ancillary services for grid stability. 4. Recent developments and future trends. Green Open Access Rules, 2022, simplify access for consumers purchasing renewable energy from DG sources. Push for smart grids and digitalization to improve DG integration and demand-side management. Energy storage policies expected to be strengthened to support DG and microgrids. Time of day, TOD, tariff implementation to encourage optimal DG utilization. Types of distributed generation, DG, grid interconnection. DG can be integrated into the grid in various ways, depending on system size, location, and operational needs. Here are the major types of DG grid interconnection. 1. Grid-connected DG systems. These systems operate in parallel with the main grid and can export power to it. Types of grid-connected DG systems. A. Net metering interconnection. Consumers generate electricity, e.g., rooftop solar, and feed excess power to the grid. They receive credits or monetary compensation based on exported energy. Example, residential rooftop solar systems in India. B. Gross metering interconnection. Entire power generation is fed into the grid at a fixed tariff, while the consumer buys electricity separately. Example, large solar plants under India's state solar policies. C. Grid-tied DG with no export. DG units generate power for self-consumption, with no export to the grid. A reverse power relay ensures no power flows back to the grid. Example, industrial captive power plants. D. Grid-connected DG with battery storage. Hybrid systems includes solar plus battery or wind plus battery systems to store excess energy. Can operate independently when the grid is down. Islanding capability. Example, smart grid projects in India integrating solar plus BESS, battery energy storage systems. 2. Off-grid, standalone, DG systems. These systems do not connect to the main grid and supply power independently. Types of off-grid DG systems. A. Microgrids. Small-scale DG networks supplying localized loads. Can operate independently or connect to the main grid during normal conditions. Example, solar microgrids in rural India, e.g., Bihar, Jharkhand. B. Standalone DG systems. Single units like diesel generators, rooftop solar, or wind turbines that power remote locations. No grid dependency. Example, telecom tower solar DG. Hybrid systems in remote areas. C. Hybrid DG systems combines multiple DG sources like solar plus diesel plus battery storage for reliable power. Used in off-grid villages, military bases, and islands. Example, Lakshadweep's solar wind diesel hybrid power system. 3. Grid interactive, islandable, DG systems. These systems switch between grid-connected and off-grid mode during power outages. Uses synchronization controls and battery storage to maintain uninterrupted power. Example, campus microgrids in India that operate in grid mode but island themselves during blackouts. Choosing the right DG interconnection type. Urban consumers. Right pointing arrow. Net metering. Grid-tied solar industries. Right pointing arrow. Grid-tied captive DG with no export. Remote areas. Right pointing arrow. Standalone microgrids. Critical infrastructure, hospitals, data centers. Right pointing arrow. Grid interactive hybrid systems.